All right, hi everyone. So it's a couple minutes after the start time, so let's get started. Welcome to week 3 of the Introduction to NLP series for Women Who Code Data Science. Thank you so much for joining. I'm seeing everyone joining from all places around the world. It's very exciting. I hope you were able to review the content from the previous weeks, and if not, you can access the recordings anytime from the Women Who Code website, and you can also find the links to the Google Colab notebooks that we shared along with the slides from the presentations. So let's, before we get started, just a few introductory things. So shout out to our amazing team of volunteers for putting together this series. We would not have this series without them. All of them are panelists on this webinar. And for this session, I will be the speaker, and all the other leaders will be present on chat to support you throughout today's seminar. And please feel free to reach out to us with any questions you may have. So I'm Rishika Singh. I did present for the first week, kind of just the NLP 101. And I'm currently a graduate student with a concentration in AI and ML. And then just a shout out to our sponsor, Home Depot, for putting together these much needed events for our community. Please do show your appreciation for them by retweeting our post, and Helena has actually shared that in the chat right now, so you can find that link there. And just before we begin, if you would like these slides, you can download them at this link here. And if you have any questions, please feel free to post them in the Q&A box, and one of the panelists will answer as soon as they're able to. And if any issues come across, please chat directly with the panelists if you're facing any issues anytime in today's presentation. So let's get started. So we'll be doing part 2 of the deep dive, and this is focusing on feature engineering, specifically TF-IDF, bag of words, and document similarity and various use cases of that. And we, in the first half, I'll be going through kind of the theory part and going over the concepts. And then we'll take a 10-minute break just to, everyone to just get up, grab some water, grab a coffee, take a breather, and then we'll come back and we'll implement it with Google Colab using NLTK and sklearn. So for today's agenda, we're just going to do a quick recap of week 2, which was deep dive part 1. Then I'll be going into deep dive 2 content, which will first be TF-IDF, then we have bag of words, and lastly we'll have the document similarity and the different use cases, and then we'll take our break and then come back and implement with Google Colab. We'll go over if there's any questions that are pending, and then we'll just do a quick wrap up and next steps. So for a recap of week 2, so we kind of introduced feature engineering and a quick overview of that. So what is feature engineering? Feature engineering refers to a process of selecting and transforming variables when creating a predictive model using either machine learning or statistical modeling, which can include deep learning, decision trees, or regression. And this process involves a combination of data analysis, applying rules of thumb, and judgment. And sometimes it's referred to as pre-processing. So machine learning algorithms cannot work on the raw text directly, and they can only process the numeric representation of the actual text. So different feature engineering techniques can be used to convert this text into a matrix or a series of vectors. And some popular methods of feature extraction are bag of words and TF-IDF, and I'll be going into both of these just after we finish up this recap of last week's material. And then we also went over some techniques to understand text. So the first one is shallow parsing or chunking. So this is a process of dividing a text into syntactically related groups. So you basically divide the whole text into non-overlapping contiguous subsets of tokens. And is very crucial for information extraction from the text to then create subcomponents such as locations or people's names. And chunking is kind of the happy middle ground that gives you enough information about the syntactic structure to reliably extract meaning from language without burdening the system with unnecessary information. And you get very nice speed and very high utility. from this process. The next one is named entity recognition. And this is when we have terms that represent specific entities that are more informative and have a unique context. Here's where you represent real world objects like people, places, organizations, and so on, which are often denoted by proper names. This is used in information extraction to identify and segment the named entities in various predefined classes. So the steps are to detect a named entity, then to extract the entity, and then to categorize the entity. And there's a few different methods for extraction that were discussed last week. So one of them is lexicon approach, then we have rule-based systems, and lastly, we have machine learning-based systems. And then the last concept from last week I wanted to go over was n-grams. So an n-gram model is a type of language model, which is about finding the probability distribution over word sequences. So n-gram means a sequence of n words. And n-grams help to kind of cut out the noise from the data in your analyses. It helps you to identify themes very quickly. And there's various applications of this, including speech recognition, machine translation, and predictive text input. So that's our recap from last week. And again, looking back at this NLP workflow, this is the stage we're focusing on right now, which is the text representation and feature engineering. So let's jump into this week's content. So first we have TF-IDF. So in the various parts of feature engineering for NLP, we're focusing on TF-IDF. And this stands for term frequency inverse document frequency. And it basically uses a combination of these two metrics, term frequency, or TF, and then inverse document frequency, or IDF. And this technique was developed for ranking results for queries in different search engines. And now it's a very, very useful model in the world of NLP and specifically information retrieval. And this kind of model actually uses a scaling or normalization factor in its computation, which I'll be going over just in a couple slides. And it has various applications. So in information retrieval, TF-IDF was invented for searching through documents. It can be used to deliver results that are most relevant to what you're searching for. So imagine if you go into Google, a very common search engine, you search for a certain keyword, the results will be displayed in order of relevance, and it'll be ranked kind of in order of relevance. And so this search engine is actually using TF-IDF to basically score the different possible results and give you the most relevant results first. It can also be used for keyword extraction. So TF-IDF is useful for extracting keywords from text, and basically the highest scoring words of a document are the most relevant to that document, and therefore they can be considered keywords for that document. So the main goal of TF-IDF, TF-IDF can be thought of as a numerical metric that reflects how important a word is in a collection of corpuses. So words that are frequent in a document but not across documents tend to have a very high TF-IDF score. The TF-IDF value increases proportionally to the number of times that a word appears in the document and decreases with the number of documents in the corpus that contain the word. So why do we use it and why does it work? So machine learning with natural languages has one very major hurdle, and that's, as I said earlier, algorithms usually deal with numbers and natural language is text. So we need to transform that text into numbers, which is known as the process of text vectorization. And so it's a very fundamental step in the process of machine learning for analyzing text. And different vectorization algorithms will drastically affect your end result. So you need to choose an algorithm that will deliver the results that you're hoping for. So once you've transformed these words into numbers in a way that machine learning algorithms can understand, the TF-IDF score can be fed into various algorithms, including naive Bayes and support vector machines, which greatly improve the results of more basic methods, like just counting up words. And why does it work? So simply put, a word vector represents a document as a list of numbers. And basically you have one vector for each possible word of the corpus. So vectorizing a document is actually taking the text and creating one of these vectors, and the numbers of the vectors represent the content of the text. And TF-IDF enables us to give us a way to associate each word in a document with a number that represents how relevant each word is in that specific document. Therefore, documents with similar relevant words will have similar vectors. And this is what we're looking for in a machine learning algorithm. So if you put this all together, we're basically looking at what is the relevant importance of a given term in a given corpus. So this is the formula that we see for TF-IDF. So term frequency specifies how frequently a term appears in the entire document. So it can kind of be thought of as the probability of finding a word within the document. So we're basically calculating the number of times a word X occurs in document Y with respect to the total number of words in the entire document. Then we look at IDF, and this is a measure of whether a term is rare or frequent across the documents in the entire corpus. So basically all the documents encompass one corpus. And IDF highlights those words which occur in very few documents across the corpus, or basically, the words that are rare have a high IDF score. And IDF is this log normalized value, as you can see in the formula here. And that is obtained by dividing the total number of documents in the corpus by the number of documents containing the term X, and basically taking the logarithm of this entire term. And since the ratio inside the log function has to always be greater than or equal to 1, the value of IDF is greater than or equal to 0 because of taking the log of that. So when a term appears in a large number of documents, the ratio inside the log approaches 1, and the IDF is therefore closer to 0. So we've put this all together. We see that TF-IDF is a product of term frequency TF and inverse document frequency IDF. And as you can, and this is the formula that we'll be referring to, and we'll also be using this to calculate TF-IDF when we do our implementation in the second half. So this is just another representation of kind of how we go through and calculate TF-IDF. So the first formula is calculating TF, where the Fij is the frequency of term I in document J, and then Nj is the total number of words in document J. And I'll be referring back to these equation 1, 2, and 3, because I'm just going to go over a very simple example of how we calculate this with an actual document. And then in this IDF, in equation 2, here we're calculating IDF. So this is where N is the total number of documents in the corpus, and Ci is the number of documents that contain that word I. And we put this all together, and we finally get Wij, which is the TF-IDF score of term I in document J. So some more properties of TF-IDF. So you basically compute it for every word in every document. And what we get as a result is a matrix with the shape of the number of words times the number of documents. So as you can see here, the number of words are, all the words are here, and here are all the documents, D1 through D5. And a single value, what you get is a single value for one word. And so you end up with a matrix of values when you're considering all of the documents. So from here, let's just move to a very simple example. So let's just say we have 3 documents here. Document 1 is machine learning teaches machines how to learn. Document 2 is machine translation is my favorite subject. And then document 3 is term frequency and inverse document frequency is important. So for step 1, what we're going to do is compute this Fij, which is the frequency of term I in document J, and we'll be using equation 1 from a couple slides ago. And so this is just pure counting. So we look at each term I in documents 1 to 3. So for Fi1 and Fi2 and Fi3, this is what we get. So we have document 1, document 2, and then lastly document 3. And we basically count up how many times each of these words occur in each of those different documents. And this is just a very pure, simple counting of every term in these 3 documents. Then we have step 2, and this is where we compute the normalized term frequency, TF-IJ, and again, we'll be using this equation 1. So each word in a single document should therefore divide the total number of words in that document. So what we end up with for TF-I1, TF-I2, and TF-I3, corresponding to documents 1, 2, and 3. And we basically go through and compute this normalized term frequency, given that these are the different terms that we counted up from step 1. Then we have step 3, and here we'll be using equation 2, and this is where we compute the IDF of each term I. So here we have all of the terms in one column, and the second column is the IDF for each of those terms. And notice that the TF actually has, the TF had 2 dimensions for word I and document J, but IDF actually only has 1 dimension, and this is just for the word or the term I that we have. And then from here we move to step 4, and now we'll be using equation 3 to put all of this together. And this is where we compute the entire TF-IDF for every word I in document J. And so you have TF-IDF I1, I2, I3, again corresponding to the 3 documents. So this can be stored as a TF-IDF index. So basically for each document we store the TF-IDF value of each term. And typically in practice, each document goes through the same steps of tokenization, filtering out the stop words, lowercasing, stemming, basically what we have done in the past with pre-processing. So we do all of that, and then we compute the TF-IDF. And just as a side note, you'll see later when we actually do the implementation, we'll be using scikit-learn, and what scikit-learn does is that it actually generates a TF-IDF matrix. And this is with the shape of n times the entire vocabulary size. So if a word in the vocabulary does not exist in the document, then the corresponding element will just be 0. And then what we end up with is a very sparse matrix. And that's what we get as an output from scikit-learn when we compute the TF-IDF score. So I'm going to take us one step further, and let's say that we're given a query. So let's say the query is machine learning, and we want to compute the TF-IDF of the query. So what we do is we have the TF in one column, the IDF in the second column, and then we put TF-IDF as the product. And we have the different terms, machine and learning, separately, and we compute this for document 1, 2, and 3. So the TF-IDF value can be treated as a future representation of the query machine learning. And this kind of helps to rank documents. And so basically we can compute a query document similarity using cosine similarity, and this will be discussed later in the presentation. But this was a very simple example of, given a query, we can compute the TF-IDF for the 3 documents that we started out with. So that's it for the theory of TF-IDF. I know that's a lot to go through, so let's just take a little breather. And next we'll be going over bag of words, which is another very common feature engineering technique, and it's very, very useful. So with that, let's jump to the next section. And that will be bag of words. So why is it called a bag? So any information about the order or the structure of the words in the document is actually discarded. And the model is only concerned with whether the known words occur in the document and not really where in the document. So a very common feature extraction procedure for sentences and documents is this bag of words approach. And in this approach, we look at the histogram of the words within the text, basically considering each word count as a feature. And the general intuition is that similar documents are going to have similar content. Further from that, just the content alone, we can learn, just from the content alone, we can learn something about the meaning of the document. And the bag of words can be, as simple or complex as you like. The complexity comes both in deciding how to design the vocabulary of the known words or the tokens, and also how to score the presence of these known words. So the bag of words model is like this. So this is perhaps the most simple vector space representational model that we use for unstructured text. So a vector space model is simply a mathematical model to represent unstructured text or any data as numeric vectors, such that each dimension of the vector is a specific feature or attribute. So the model's name is such because each document is literally represented as a bag of its own words. And this is disregarding the order of the words, the sequences, and the grammar. And it's one of the most fundamental methods to transform tokens into a set of features. And the model is used in document classification, where each word is used as a feature for training the classifier. So for a very simple example, if we had a task of looking at sentiment analysis for reviews, we can look at the presence of words like fabulous and excellent could indicate a positive review, whereas the words like annoying or poor would point towards a negative review. So the bag of words model represents each text document as a numeric vector. And this is where each dimension is a specific word from the corpus. And the value, could be its frequency in the document, the occurrence typically denoted by 1 or 0, this binarized value, or even a weighted value. And so there's typically 3 steps while creating a bag of words model. So first is just the text pre-processing. And this is where we convert the entire text into lowercase characters, you remove the punctuation, you expand the extractions, you remove unnecessary symbols, tokenization, etc. The second step is to create a vocabulary of all the unique words from the corpus. And lastly, in the third step, we create a matrix of features by assigning a separate column for each word. And while each row corresponds to that specific document. And this process is known as text vectorization. So every entry in the matrix signifies either the presence or the absence of the word in the review. So we put 1 if the word is present and 0 if it's not present. So just like I did for TF-IDF, we're going to just do a very simple example of how we kind of go about with actually implementing a bag of words model. So we're going to take a very simple example. This is a snippet of the first few lines from the book A Tale of Two Cities by Charles Dickens. And so we just have, it was the best of times, it was the worst of times, it was the age of wisdom, it was the age of foolishness. So as I said, step 1, we're just going to collect the data. And what we're going to do is that each line of the 4 lines, is treated as a separate document. So basically these 4 lines are the entire corpus of these 4 documents. Then in step 2 is where we design the vocabulary. So we will now make a list of all of the words in our model's vocabulary. Only the unique words here is what we're concerned with. So we're going to be ignoring case and punctuation. So what we end up with is, it was the best of times, worst, age, wisdom, foolishness. So in our list, we have this vocab of 10 words, and we initially had a corpus of 24 words. So as you can see, we've already removed more than half to obtain our vocab of just only the unique words. Then in step 3 is where we create the document vectors. So the objective here is to turn each document of free text into a vector that we can use as either the input or the output for a machine learning model. And because we know the vocabulary has only 10 words, we can actually use a fixed length vector or document representation of 10, where 1 position in the vector is to score every word. And the simplest scoring method is to basically mark the presence of words as this Boolean value, either 0 for absent or 1 for present. And using the arbitrary ordering of words listed above listed right here in our vocabulary, we can actually step through the first document, it was the best of times, and convert it into a binary vector. And so the scoring of the document would look as follows. So it was the best of times, all of these appear, so they get a 1. And then worst, age, wisdom, foolishness, these 4 do not occur in this first document, so they all receive a 0. And so we can represent the first document as this binary vector, and we basically repeat the same process for the other 3 documents as well. And all ordering of the words is discarded, and we have a very consistent way of extracting the features from any document in our corpus, and so that they're ready to be used in our modeling. And new documents that overlap with the vocabulary of known words, but they also might contain words outside of the vocabulary, and they can still be encoded, where only the occurrence of the known words are scored, and basically the unknown words are completely ignored. And you can kind of see that as we scale to larger vocabularies and larger documents, this entire process will naturally scale to that level. So next, we're just going to be looking at how we kind of manage our vocabulary. So as the vocabulary size increases, so does the vector representation of the documents. And so as you saw in the previous example, the length of the document vector was equal to the number of known words. But you can imagine that for a very large corpus, such as thousands of books, the length of the vector might be thousands or millions of different positions in that single vector. And further, each document may contain very few of the known words that are in the vocabulary. And so this can result in a vector with lots of zero scores, and this is typically called a sparse vector or a sparse representation. And this is a very big issue because it requires more memory and computational resources when we're actually modeling, and the vast number of positions or dimensions can actually make the entire modeling process very challenging for some traditional algorithms. So as such, there's a kind of a pressure to decrease the size of the vocabulary when we're using a bag of words model. And what we can do is just go through some text cleansing, and there's various techniques like ignoring case, punctuation, ignoring stop words, fixing misspelled words, and stemming. And this is all what we went through in the first 2 weeks of how we kind of go through this text pre-processing, and that can vastly help this issue of the way that we get a sparse vector representation. So that's what we have for the theory for bag of words. Again, we're just going to take a quick breather because I know that's a lot of content. So now our next, our last stage of our theory part will just be going over some document similarity and the different use cases. So for document similarity, this is a process of using a distance or similarity-based metric that can be used to identify how similar a text document is with any other document or documents. And this is based on features that are extracted from the documents like bag of words or TF-IDF. So you can see that we can kind of build on top of these TF-IDF based features that we have engineered in the previous section, and use them to generate new features, which can be very useful in domains like for search engines or document clustering and information retrieval. And this is done by leveraging the similarity-based features. So document similarity, as the name suggests, is just how similar are two documents. And when I refer to documents, is just kind of a collection of strings. That's what encompasses a single document. And the document similarity is calculated by calculating document distance. And document distance is a concept where words or documents are treated as these vectors, and you actually calculate the angle between two given document vectors. And these document vectors are the frequency of the occurrences of words in any given document. And the measure of similarity can be either qualitative or quantitative. So in qualitative, the assessment is done against subjective criteria, which can include theme, sentiment, overall meaning, etc. And then in quantitative, numerical parameters such as the length of the document, the number of keywords, common words, etc. Those kinds of parameters are actually compared between these two documents. So this entire process is carried out in 2 steps. So the first step is vectorization. And this is where we transform the documents into a vector of numbers. And some of the most popular number representations that we get, or these measures, are TF-IDF. And then the second stage is distance computation. So we actually compute some sort of similarity measure one of them being cosine similarity, which is one of the most popular ones chosen. And we just compute this value between the document vectors. And so specifically for cosine similarity, as we know, the cosine or the dot product of the same vectors is going to be 1. Very dissimilar or perpendicular vectors, they're going to have a cosine of 0. And so the dot product of two vector documents is some value between 0 and 1. And this is a measure of similarity amongst those documents. And so pairwise document similarity in a corpus involves computing document similarity for each pair of documents in that corpus. So thus, if you're given, if you have C documents and D documents in corpus C, then you would end up with this D times D matrix. And this is where each row and column actually represents the similarity score for a pair of documents, which represent the indices at the row and the column respectively. And so, as I said, there's various similarity and distance metrics that can be used to compute document similarity. These include cosine distance or similarity, Euclidean distance, Jacquard distance, Manhattan distance, and so on. And so we're actually going to be going over just a few of these different use cases. So as you can see here, we'll start out with just the Euclidean distance, then we'll go into cosine similarity. Then we'll go into Jacquard similarity, and then we'll have document clustering with similarity features. And lastly, we'll have topic models. So these are just 5 different use cases of the concept of document similarity. So let's jump into the first one. So this is where we actually compare the shortest distance among 2 objects. We use the Pythagorean theorem. And the output is a score, and the score is basically the distance between 2 objects. So if the score is 0, it means that both objects are completely identical. So it's a very simple calculation, and we'll be going through all of these calculations when we actually implement with Google Colab in the second half. And then some limitations, however, is that even if 2 similar documents are far apart, according to Euclidean distance, due to the size of the document, chances are that they may still be oriented closer together. So a smaller angle can actually mean higher similarity. And so here we have a visual representation of Euclidean distance. So D is Euclidean distance, and here we actually have the cosine similarity, or theta. So while the cosine angle, looks at the angle between, the cosine looks at the angle between the 2 vectors. So we're not actually taking into regard their weight or their magnitude. The Euclidean distance is actually similar to kind of just using a ruler to just measure the distance between A and B in this case. And so cosine similarity is generally used as a metric for measuring distance when the magnitude of the vectors does not matter. And so this can happen, for example, when working with text data that's represented by word counts. And text data is the most typical example for when to use this metric. So from here, we actually move to cosine similarity. And this is where we determine the angle between 2 objects to find their similarity. And the range of the scores, again, between 0 to 1. So if score is 1, it means that they're the same in orientation, but not in magnitude. And that's what's the difference between cosine similarity versus Euclidean distance. So cosine similarity basically gives us a metric representing the cosine of the angle between the feature vector representations of the 2 text documents. So the lower the angle between the documents, the closer and more similar they are, as you can see in this figure. So if the angle is very close to 0, the cosine similarity score is very close to 1. And so therefore, the vectors u and v are very similar to each other. And then here we have the angles very close to 90. And so this means that they're basically perpendicular to each other. And so the cosine similarity score is close to 0, meaning vectors u and v are not similar to each other. And then here we have the angle is very close to 180 degrees, and the cosine similarity score is close to -1. So the vectors u and v are completely unrelated and actually in opposite orientation to each other. But typically we just kind of keep the range of the score between 0 to 1 and disregard any value lower than 0. So for cosine similarity, we compare the pairwise document similarity, and this is based on the TF-IDF feature vectors. So here we actually use the cosine similarity function of sklearn, and we basically call this function on the matrix of the vectors in our TF-IDF calculation. So this is just a sample table of the similarity matrix. So as you can see, it looks like, you know, documents 0, 1, and 6 are, and 0, 1, and 6, and then 2, 5, and 7 are actually very similar to one another. And documents 3 and 4 are slightly similar to each other, but the magnitude is not very strong. However, still stronger than the other documents that we have. And so this is a very nice example of grouping or clustering of the documents that can actually be solved by unsupervised learning. And this is especially useful when you're dealing with a huge corpora of millions of text documents. And again, we'll be implementing this cosine similarity after we compute our TF-IDF feature vectors. So the next similarity measure use case that we have is Jacquard similarity. And so this measurement is referring to the number of common words over all the words in the documents. So more common, more common means that both objects should be similar. So here we actually take the intersection of A and divided by the union of, the intersection of A and B and divided by the union of A and B. And here in this case, we have A and B as two different documents. And again, the range of the score is between 0 to 1. And so if we have a score of 1, that means they're completely identical. And if the score is 0, that means that there's no common word between the first sentence and the last sentence. So the score is 0. And then next we have document clustering. So what document clustering does is that it leverages unsupervised learning to actually group the different data points. And in this case, the data points are documents. And it groups these documents into groups or clusters. And so we'll actually be leveraging an unsupervised hierarchical clustering algorithm to group similar documents from our corpus by leveraging the document similarity features that we, would have already generated at that point. And so just in a broad sense, there's two different kinds of these hierarchical clustering algorithms, which are either agglomerative or divisive. And we'll actually be using the first one. And this is kind of using this like bottom up approach. So what you do is that each observation or document actually starts out in its own cluster. And then the clusters are then successively merged together using a distance metric. And this distance metric, measures the distances between the different documents. And we actually use a specific linkage merge criterion. And a lot of this is kind of just done under the hood, and we won't be doing a lot of this from scratch. We have some nice algorithms that we can very easily implement, with Google Colab, and I'll be walking through this process. And so this is just a sample depiction of this agglomerative clustering algorithm that I just explained. So, we start out with A, B, C, D, E, F as these different data points or these documents, and successively we try to, depending on their distance metric or the similarity measure, we basically are able to see, oh, B and C are similar, so those get grouped together. D and E are similar, those get grouped together. Then we actually see that F ends up getting together with D and E, and then we group these two together, and eventually you get all of them, all 6 at the end. So our main strategy in document clustering is actually how we select this linkage criterion. There's different kinds of examples of this linkage criterion. It can be words, complete linkage, average linkage, and so on. So, and this criterion is very useful for choosing the cluster pairs that we would like to merge in each step. And this is based on the optimal value of an objective function. And the pair of clusters are these individual documents at the lowest step, and then the clusters in the higher steps. And so in our implementation, we'll actually be choosing the Ward's minimum variance method. And this is our linkage criterion that we select. And this is basically where we would like to minimize the total within cluster variance after we go through the merging. So therefore, at each step, we actually find the pair of clusters that leads to the minimum increase in the total within cluster variance after every merging step. And since we already have our similarity features, we can actually build out this entire linkage matrix on our documents. And so this is an example of a linkage matrix. And if you look closely here, you can see that each step or row of the linkage matrix actually tells us which data points or clusters were actually merged together. And so if you have n data points, then the linkage matrix will be having a shape of n minus 1 times 4, where every component of this matrix will actually tell us which clusters were merged at that specific step. And so here we have each row has 4 elements. So the first 2 elements are either data point identifiers or the cluster labels. The third element is the actual cluster distance between the first 2 elements. And the last element is the total number of elements or data points in that specific cluster once this merging step is complete. So that's kind of how we step through this process. And so every row is just every merging step that we're taking to eventually cluster all of these documents. And a nice visualization that we end up with is this dendrogram. So it's this hierarchical clustering dendrogram, and it helps you to just understand the elements a lot better. And so we can see how every data point starts out as an individual cluster, and then it slowly starts getting merged with the other data points to form the clusters. And so on a very high level, from the colors and this entire diagram, you can see that you end up seeing that the model can very nicely identify how many clusters. And so in this case, we actually have 3 major clusters, and this is after you consider a specific distance metric. And so from here, we actually can leverage this distance metric, and we can actually get our cluster labels. And so with specifying that the distance metric has to be greater than 1, we can obtain our cluster labels. And so thus you can clearly see in this specific example, all these documents were already categorized in advance, so by weather, animals, and food. And so in this case, you can actually see that the algorithm was able to correctly identify that there were these 3 distinct categories in all of these 8 documents, and based on the cluster labels that were assigned to them. So as you can see that for document 0, 1, and 6, those were all categorized as weather, and they all had the cluster label of 2. Then you can see for 3 and 4, those had the category of food, and they were given a cluster label of 0. And lastly, for the third category of animals, you can see that they documents 2, 5, and 6 were categorized as animals, and they had the corresponding cluster labels of 1. And so, this is a very useful pipeline to cluster your documents. And that kind of, this should give you a good idea of how our TF-IDF features are able to be leveraged to then build the similarity features. And this in turn helped to cluster all of our documents. And this is done in a very nice, quick, and accurate process. And then the last use case of document similarity that we have is the topic models. So we can use some summarization techniques to extract the topic or the concept-based features from our text documents. And so the whole idea of topic models is around the process of extracting key themes or concepts from a corpus of documents, which are then represented as topics. And so each topic can be represented as a bag or a collection of words or terms from our entire document corpus. And so together, these themes, these terms help to signify a specific topic, theme, or concept, and each topic can be very easily distinguished from other topics simply by the virtue of the semantic meaning that is conveyed by these terms. And sometimes, however, you do end up with overlapping topics just based on the data and based on the task that you have at hand. And so that's an important thing to keep in mind. And these concepts can range from very simple facts and statements, or it can be very subjective opinions or outlooks. So that's another very important thing to keep in mind. And topic models are extremely useful in summarizing a very large corpus of text documents that you might have. And this is, it's very useful because we can actually extract and depict key concepts. When you have a very large corpus where it's, not very readable to go through every single line in all of these documents. And it kind of gives you a very nice high level understanding of what are the key concepts. And so there are various techniques for topic modeling, and most of them involve some form of a matrix decomposition. And some of these techniques, we have latent semantic indexing, or LSI. This uses matrix decomposition operations, more specifically singular value decomposition. We will actually be using another technique, which is called latent Dirichlet allocation, or LDA. And this actually uses a generative probabilistic model where every document consists of a combination of several topics, and each term or word can be assigned to a specific topic. So the math behind this technique is pretty involved. The black box in this figure actually represents the core algorithm that is used, and it makes use of different parameters, and basically we try to extract K topics from M documents. So this is a very black box algorithm, and I chose to not include it here just because it's a bit more advanced, but I do have a link to where this was, where I got this diagram from, where it does go a little bit further into the algorithm if you would like to do some further reading on that. So basically, once this algorithm is run for several iterations, we should have these different topic mixtures for every document. And then from there, we generate the constituents of each topic from these terms that are pointing to that specific topic. And we have several different frameworks, like scikit-learn has a very nice way where we can leverage this LDA model for generating topics, and that's what we'll be doing towards the end of our implementation. And so when we have LDA, this is decomposed into two different components. So we actually have document topic matrices and a topic term matrix. And so the document topic matrix is, it would be like the feature matrix that we're looking for. And then the topic term matrix helps us in looking at the potential topics in the corpus. So we'll be leveraging scikit-learn for obtaining this document topic matrix. And this is just an example of this matrix. And you can very clearly see here, which documents contribute the most to which of these three topics, T1, T2, and T3. And you can also, view the topics and their main constituents. And so you can clearly see that, in this case, we have these three topics. They're quite distinguishable from each other based on their constituent terms. And in the next step here, let me see. Okay, yeah, so it's not shown here, but basically you can, see the actual terms that are in each of these topics. And basically you can see that the first one is generally talking about weather. The second one is generally talking about food. And T3 is generally talking about animals. This is just the same ongoing example from the previous slides. And so choosing the number of topics for topic modeling is an entire different topic on its own. And it's actually a very complicated process. And so there's various methods and heuristics to get the optimal number of topics. So what's been done here is actually the bag of words model-based features have been used to build the topic model-based features, and this was done using LDA. And so what was actually done is you leverage the document term matrix that was obtained, and then you use the unsupervised clustering algorithm to then try and group the documents that are similar to what we did earlier with our similarity features. And so what was done here was a very popular partition-based clustering algorithm was used, and that's the k-means clustering, which possibly some of you might have heard from before. And so k-means clustering is actually where we cluster or group these documents based on their topic model feature representations. And so in k-means clustering, generally we have this input parameter, little k, and this is what specifies the number of clusters that it will actually output, and this is done using the document features. And so this clustering method is a centroid-based clustering method, and this is where you actually try to cluster these documents into clusters of equal variance. And so you try to create these clusters by minimizing the within cluster sum of squares measure. This is also known as inertia. And there's multiple ways to try to select the optimal value of this little k parameter, which is your input parameter. And I believe we'll actually be using the elbow method, which is, not to go too much into that, but that's something that sklearn is we can actually leverage that and actually get that computation. And so you can see here from this example that our, these 8 sample documents that we have, they were correctly assigned to the right clusters, just like it was done for our previous use case when we just used a simple similarity metric. So that's it for the document similarity. Now that's it for our theory. So I'll just do a quick wrap up, and then we're going to be taking a 10-minute break before we jump into the implementation with Google Colab. So I'll just take another little breather. We made it through all the theory. I know that was a lot, but now we get to actually code and actually see all of these put to work and see exactly, how do they work. And so just for a quick recap, so we went over TF-IDF, we went over the bag of words model, and lastly, we just went over various use cases of document similarity, including different similarity metrics like Jacquard similarity, Euclidean distance, and cosine similarity. And then we took it a little bit further and we went into how do we cluster the documents using the different similarity measures, and we also went into topic modeling. So now we get to actually implement all of these, and we'll be doing that with Google Colab. You can find the link right here. And that's just been shared by Helena in the chat. And so now let's just take a 10-minute break. So it's on, well, for me, I'm in California. So for me, it's 1:25. But basically in 10 minutes, we'll resume and we'll get into the implementation. And I hope everyone can just get up and take a breather, grab some water or coffee, and we'll be back in 10 minutes. Thanks, guys. All right. Hi, everyone. I hope you enjoyed that 10-minute break. Just as a reminder, we do have the poll that was sent out, and I believe there was information given about that. And so now we will be jumping into the a Google Colab project. So let me just, okay. So we will, so if you click on this link here, it will direct you to the GitHub repository that we have for Women Who Code. And this is the notebook that we'll be using. So in order to open this directly in Google Colab, what you can do is just type in, Google Colab. And from there, it'll directly, it'll direct you here. And what you can do is go into GitHub. I believe it's just waiting for authorization. Okay. And so what we can do is take, let's see here. Take this link and, okay. Take this link that we have here, copy that and paste it in here. Let's see. Why is this not showing up? Let's see. Okay, let me actually go directly to, so what we'll do is actually click on this, the direct link for the notebook. And I believe that should work. So let's look here. Okay. And so now we have that notebook opened up. And so I hope everyone is able to do that properly. And so I actually just had to have the notebook open in advance because I wanted to just have this data set loaded in advance because it just does take a little bit of time. So here we'll be doing our code implementation for the 3 topics that we went over in the theory section. So first we'll have TF-IDF, then bag of words, and lastly our different use cases for document similarity. And the data set we'll be using is actually the same data set that Jaita used in last week's session. So we just wanted to maintain that consistency. So if you click on this link for the data set, it will take you here. And this is actually a data set hosted by Kaggle. And if you want to read up afterwards, there's just some more information about the data set, kind of just giving some context, exactly where were these publications taken from, New York Times, Breitbart, CNN, etc. And we'll actually be using only one of these CSV files, and that's the articles1.csv. And this is 50,000 news articles. So what you can do here, there's some steps that are outlined in the notebook itself, but basically what you can do is click on the data tab. And then we want to go down here and we actually want to just download this articles1.csv. So we can simply download that and then it'll be downloaded as a zip file. And I've already kind of gone through this process, but just to show you guys. So we click on that, which will automatically unzip this file, and then it'll be saved. And so a good place to save it is somewhere that you can remember, because you will actually be needing to know that location when you come back to this notebook. So basically it'll open up automatically, probably in downloads, but what you can do is save it into documents or a specific folder or on your desktop, wherever you remember that you're saving it to. And then now we have this Google Colab notebook open. What you want to do is click this here to upload the file. And basically this is the articles1.csv that I have. And I've already uploaded, so I'm not going to do this, but basically you just select that and then press open, and it would start to upload it here. And once it's uploaded and in place, then it'll show up just in this. So when you open the notebook, there'll be this navigation pane on the left-hand side. So this is the table of contents. This is just some code snippets, and lastly, we have our file system, and this is where you'll see the data set that's been uploaded. And so the data location of this is actually in content, and inside the content is also the sample data that just automatically comes with the notebook. And then we have our articles1.csv. And so with this PWD, what we can do is just check, which folder are we actually in this notebook. And so we know that we're in content, and that's where we need to be in order to get to our file. So now using ls, we'll list everything that's inside the content directory. And so here we have the articles1.csv and sample data. And this is kind of what Jaita had in her notebook from last week as well, but I just wanted to include that here just to give everyone enough context. So now we will enter in loading our data set and then do some EDA and pre-processing. I won't go into too much depth in this because this was reviewed by Jaita in the past, and also when I did the first week with pre-processing, but I just want to include that here just to give everyone enough context. So basically, this is the code that we'll be using to actually load the CSV into a pandas data frame. And we want it to be in a data frame because it makes it far easier to work with this data and do what we need to do. And I did actually slightly edit this CSV file. Simply what I did is that I added a label to this column called num. And the reason why we're doing that is because we're actually only going to be looking at the first 10,000 rows of this in place of the full 50,000, just because it is a little bit hard to go through all 50,000, and it just takes a very long time for it to process. And even with like a sped up runtime, it just makes it a little bit harder to go through everything. So that's why for just, for simplicity's sake, we're actually just going to be using the first 10,000 rows. So as you can see here, we have specified the different columns. So num, ID, title, publication, etc. Then we're going to be reading it in using this read_CSV function that pandas allows us to do. This is the name of our CSV file. We're using Python. The columns that we want to assign to the data frame are what we have inside here, this variable columns. And then we're going to be choosing the first 10,000 rows. And so let's just run that, and it'll load it in. And we actually get this nice printout of there's 10,000 rows and 10 columns. And then we actually go through and make sure there's no empty columns. And we just get a second printout just showing, we have removed all the empty rows, and we still have our 10,000 rows and our 10 columns. And so this code here is actually helps to remove any sort of bad lines that we have, and we actually do that using this column num. And so we basically, if there's like some sort of bad link or any sort of error that might be corrupting our file in any way, we want to just get rid of that. And so we just try to simply remove it from the data frame. And so basically let's just run that and make sure we get rid of anything that might be corrupting our data. And so that is it for loading in our data set. And so now let's move to just a simple looking at our the description of the data set. So let's look at this. We can basically just do news articles df. That's what we have named our data frame, and then .info. That just gives us some information of this is how many columns we have. These are the label of the columns. How many null values do we have, and what is the data type of each of these. It also shows you this is how many different data types we have. So float 64, int 64, and then some objects, and then also how much memory is being used. And then this here we basically call the same data frame, and we do the .is null, and that basically will tell you if there's any null values, and we just basically just do .sum on that. So let's run that, and we can see that there are some values that get added up in there. And this is again just a repeat of what Jaita kind of walked us through last week. I just wanted to include that in here. And so this is a very simple visualization, and we're just looking at the different news publications names and kind of how many articles are actually in those publications in the entire data set. So we basically just use matplotlib, a very nice plotting library. We use our data frame, and we're looking at the publications on the x-axis, and then the counts of the number of articles from these publications on the y-axis. So let's just run that, and we can see this nice printout. And then we have, this is a visualization of the news articles count per year. I won't go too much into that, but just another nice visualization. Then let's look at a visualization of the news article count that was released monthly to see, you know, if there's any sort of pattern. There might be some major, you know, events that might have occurred, and we can kind of get this as a nice visualization. Next, we have the news article count per month year. So now we have the months, every single month for all of these years going up to 2017. Okay, so I see a message about not being able to have the num column. So that's something that you actually, once you download the data set from Kaggle, going through this process as I described, what you'll need to do is actually open it. It'll, depending on your system, it might open up in Microsoft Excel or Numbers, which is what it might open up in if you have a Mac computer. And basically, the num column already exists there. So if I scroll up really quick just to show you, so this, all these 0, 1, 2, 3, 4, that's already there, but there's no label assigned to that column. So you'll have to actually manually go there and just type in NUM in all lowercase. So then when you actually refer to it here, the pandas will know that this column is referring to this, and that's actually what we use to remove any of these corrupted lines that might be in our data frame. So I hope that clarifies that question. So let's get back to that. So we finished our visualizations, and now let's look at, so last week, Jaida looked at only the titles, and since we're kind of looking at document similarity, topic modeling, all of that, I actually chose to look at the content of each article. So what you can do is, we're going to be initializing a new data frame, and this is looking at only the content column. And so we basically have this new data frame, content_df. We're basically looking at our original data frame, but taking only the content column. Basically, do it to a data frame, and let's just print that out real quick just to see, okay, we got our 10,000 rows and it only got one column. We didn't want the rest of the 9 columns. And here's just a another visualization of the length of our different columns. This just shows you the content length and how many articles are of that length. So as you can see, most articles are less than 20,000, very few are 40,000, and not much beyond that. So now let's get into the part of speech tagging. Before we start that, let's just import our libraries. So again, we'll be using NLTK. I'm also be using our tokenization packages in that library. So let's just import those, and it should, just download them and unzip them, and so they're ready to go. And we'll actually also be using the contractions library, and this is for contraction mapping and to help with expanding our contractions. So we're going to first use pip to install, and then we're going to import it so that we can use it. And that ran successfully. And so now let's actually do the first step of expanding the contractions. So what we're doing here, this is the same code that we've used in the first and second week of how we go through the contractions and how we actually go through in expanding them. So we're going to be using this lambda function, and then basically this contractions library has a .fix function that we can use, and it basically iterates through every single word in all of these 10,000 rows of our articles. So let's just run that. It might take a little bit of time because there are 10,000 rows and it has to go through every single word. So let's just give it the time it needs for that to run. And so basically after we do this, then we actually are going to be joining back all of these. It basically outputs a list of items into one string, as you can see here. But we want to kind of join it back into a single string, because that's what we're going to treat all of these as just a series of strings. And so we basically use the .join function, and we're basically going to be mapping it and going over every single row in our content column. And so let's just run that. And again, this is the same code as before, so there's nothing new here. And then if you want to just look at, what does an individual cell look like, this is kind of what it prints out. And so we were able to expand all of our contractions. Next, we have our noise cleaning. This is another step of our text pre-processing. So he'll be actually dealing with our white spaces, our special characters, and our lowercasing. So here we're going to be going through the content column again. We're going to be lowering all of them to be lowercase, and we're going to be going through these different ones to actually remove any special characters. So let's just run that. And okay, so that's done. And here's just like some explanation about this, the regular expressions that was used here. So here are the different components that were used. So this this basically matches everything, but everything inside the block quotes that we have. And then the \W helps to match any word character. The \D helps to match a digit. \S helps to match any white space character that we might have. And then the quotes basically matches the character. So this is just, and it's case sensitive. And then lastly, we have the plus sign, and that helps to match between 1 and unlimited times, basically as many times as possible, giving back as we need it. And then next we have our tokenization, and here we'll be leveraging NLTK. So basically we're going to be calling this .apply word_tokenize. So that will help to tokenize, and we basically will add a second column to our content data frame called tokenized content, so that you'll be able to see kind of how is this tokenization working, how does it look different from our original content that we had. And so this might take a little bit of time. Let's just let that run. The next thing we'll be doing is going through the stop words and basically removing all of the stop words. And NLTK has a very nice and convenient stop word library that we can basically just download and utilize. Okay, so now it's all tokenized. Perfect. That's what we wanted. And now we can remove the stop words. So first we have to download this before we are able to use it. Okay, and it's downloaded. And now before we actually remove the stop words, just to kind of see like what are the occurrences of the stop words and the content of the articles itself. So we can actually plot that here and get a nice visualization. You can see just some of the most common stop words. So the appears nearly 600,000 times, all the way down to on is printed out almost 100,000 times. So it just gives you like a nice idea of, you know, what is the content of these articles. And here we can do another just further analysis. Let's just let that run a bit. Of kind of the most common words. You have Mr. said Trump would want new, and basically the count of each of those words. And so now we can actually go and remove the stop words. So here again, we'll be adding a another column. So once we actually remove, you can see the full code here. So we're actually looking at the stop words library that NLTK has. Basically go through each of these, remove the stop words, and then we add another column called tokenized content join, which will basically go through and help to actually join everything actually after we remove the stop words. And as you can see here, it joins everything after moving the stop words. And this column, tokenized content join, is the column we'll be using when we go to our next step of TF-IDF, bag of words, and document similarity. And then this is just another thing that was implemented for when Jaitha had her code from last week. And this is basically, and then this yellow brick basically helps to visualize the parts of speech tagging that we achieved through this piece of code. And so let's first just install that, and then let's actually create a visualization using yellow brick, and it'll help to actually see what are the different parts of speech that are tagged. So as you can see, you have noun, verb, adjective, adverb, etc., and exactly what is the count of each of these. And as you can see, the noun is, you know, the most common, nearly, you know, more than 3,000, all the way down to, well, some of these don't have much, but, you know, all the way down to non-English is, you know, very, very low. And this is just, you know, some examples of the different tags that we have, like what is their meaning, and kind of just some examples in English. So now that we're done with all of our pre-processing, now we kind of are up to speed on that. So let's jump into our TF-IDF. So just as a reminder, TF-IDF stands for term frequency inverse data frequency. And so this basically gives the frequency of the word in each document in the corpus. And so here we have the ratio of the number of times that the word appears in a document compared to the total number of words in that document. And it increases as the number of occurrences of that word within the document increases. And every document will have its own TF value. Secondly, we have our inverse data frequency, and this is used to calculate the weight of the rare words across all documents in the corpus. And so the words that occur rarely in the corpus have a very high IDF score, and it is given by this equation below. Just as a quick reminder to make sure we know what we're calculating. So we end up combining these two, and we could get the TF-IDF score, and this is WIJ for the word in a document in the corpus, and it's a product of TF and IDF. And again, we're taking this log of the IDF value. And so sklearn or scikit-learn actually allows us to very nicely and easily automate this entire calculation process, and has a very nice built-in capability to calculate TF-IDF. So, and here's just a quick link to just refer to some documentation if you would like some further reading on exactly this, the vectorizer that we're using here. So just as a simple example, I'm gonna take just a small subset of the articles just so we can kind of run it through, because going through all of these 10,000 is quite a bit. So I also want to do take a small amount so we can actually run through the code, and we won't have to sit here for too long for the code to finish running. So what you first want to do is import this library. So this is the TF-IDF vectorizer, and again, use NumPy. So let's just run that. And then here, this is how we actually use this vectorizer. So what we do is, just to make it simple, since the tokenized content join is a column of interest for us, because that's the column that's gone through all the necessary pre-processing, we'll be using that specific column, and I'm just going to call that text_content, and we're going to be continuously using that from here on out. And then this, we basically are going to assign this TF-IDF vectorizer the variable name of vector, and inside here we can specify some parameters, and some of these include dropping words that occur in more than a certain percentage of the documents. So the max TF here is 0.3 or 30%. You can kind of tweak these parameters however you want. I've just chosen these to be like this. These are the more common values that are used. Then you can use the words that appear at least X times. The minimum DF is 8. So if it appears at least 8 times, then you use these words. And you can actually remove stop words inside this vector as a parameter. I just left that in here, even though we already did it, but you can include that in here. Then we actually want to convert everything to lowercase. You can actually specify that parameter as well. We want to be using IDF, so we set that to equal to true. Then we also want to have our normalization, and then we also want to set this value to true, because this helps to prevent any divide by zero errors. And in this documentation, you can see what other sort of parameters you can specify. This is what I've chosen for this case, but feel free to add any other parameters that you might like to. And so, as I said, we won't be going through all of the 10,000 articles, because that's a lot to run through. So we're going to just be taking the first 10, and I'm basically just calling it as another subset of it. And the way that we actually call our vectorizer is we do our vector is what we specified up here, and we do a .fit_transform. And this content subset is our subset of 10 articles that we would like to run it on. So let's do that, and that ran pretty nice and quickly. Then we want to actually convert this to an array, and then we would like to set our vocab is basically the feature names. And this .get feature names, if you read a little bit further in the documentation, will actually give you our full vocabulary that we get from our vectorization from TF-IDF. And then I actually just called it as another new data frame, TF-IDF_data frame, and that basically nicely prints out everything. And what we specify here is actually our columns is our vocab. And so as you can see here, it's even just for 10 articles, it's quite big. But you can see this is towards the end of it. We have white, whiteman, wife, wild, willful, all of that, and you can basically see all the different scores for it. And then this is just, we called a shape on that just to see here. You can also see that number here, but basically we have 10 rows, which is our 10 articles, and 2,045 columns, which is all the words that we have in our vocabulary. And this is just printing out the vocabulary. And as you can see, it's very, very large, but you can just go through and see, what were all of the unique words that we extracted from our 10 articles. So that concludes for TF-IDF. I did only a small subset. I only did 10 out of our 10,000. and even our 10,000 wasn't the full 50,000, but that's just, you know, for simplicity's sake and for time's sake, it would take quite a long time to actually run through all of these. So, but you can very easily just modify how you're specifying exactly how many, you know, what subset of articles you want to choose. And you can leave everything else the same, and you can just change this these numbers inside here, and you can still run the same TF-IDF and get your calculation and your vocabulary. So that concludes it for TF-IDF, and now let's get into bag of words. So just as a nice reminder, this is what our raw text looks like, and then our bag of words vector actually ends up like this. So we basically go through each of these, take out the unique words, and get this kind of you know, this numerical value in the second column corresponding to each of these words. And so in here, I'm actually just gonna be taking the first 5 news articles, because this one actually takes even longer to actually successfully run. And so even taking 10 actually took quite some time. So here I'm just going to be taking 5 articles at random, and again we're going to be using this specific column, and I'm going to just this dot sample 5. The dot sample is just the function to take random values, and we specify 5 as because that's why we need the 5 articles specifically. So this is the 5 articles that I randomly chose. You can see it printed out here. We have the 5 different IDs referring to these 5 different news articles. And so for bag of words, we're going to be using the count vectorizer from sklearn. So we basically import that here, and then just like we did above, where we kind of assigned a label to this vectorizer, we're just going to call it vectorizer BOW, and that basically is just, you know, bag of words. So just to keep track of it. So we did that, and now we're actually going to be again here. I'm actually just for how I wanted to kind of name my variables, I call this corpus bag of words. That's referring to this content DF random, basically the 5 random news articles that we selected. And then our xbow is going to be equal to actually the same thing we call it dot fit underscore transform on the 5 random news articles. So let's just run that. That ran pretty quickly, and now we're just going to be printing out all of the vectorizer, all of the feature names. So basically what we end up in our vocab, and this is all of them. As you can see, it's pretty big, and here I can print out the shape, and as you can see, we have our 5 news articles, which is all of our 5 rows, and then we have 1,249 columns. And then this is basically just converting it to an array, and this is kind of what the array looks like. It's very large, even just for 5 articles. And then this is just basically the document term matrix that I referred to that we would like to output. This is what it outputs as, and it's basically we're calling it .toDense because this is a very sparse matrix, and this helps to visualize it in a more comprehensive way. So now I would like to repeat the analysis, but with a larger subset of the data, basically going through the same process of extracting only the tokenized content join column. Then we take a subset of 100, and then we call the same vectorizer with the dot fit transform. We get our feature names, which is our all these different values in here. We get a shape of this much, and this is what our array looks like. And so, you know, you can very easily just change the numbers inside here. If you would like to choose 50 articles, if you'd like to choose 1,000, feel free to. One tip I have is that an option in Google Colab, if you select a runtime and go to change runtime type, you can actually change your hardware accelerator. And I would highly suggest to start out with the GPU, because that does help to run things a bit faster. And you might get a notification like, oh, your runtime is GPU and you're not quite using it. But once you start to load in more and more data and calling all of these vectorizers on there, it will be using that GPU. And so I highly recommend that you switch to that runtime type. And so that kind of summarizes the bag of words that we have. And so our last implementation will be our document similarity. And just as a reminder, we have our 5 use cases: Euclidean distance, cosine similarity, Jacquard similarity, document clustering, and topic models. So our Euclidean distance, Just as a reminder, we're just looking at this very simple calculation using Pythagorean theorem. And so scikit-learn has a very nice Euclidean distances library that we can just import. So we imported it. And just as a reminder, we actually are going to be using our TF-IDF subset. So if you look up here, if you go back up to TF-IDF, this is our what we ended up with, right? So that's what we want to be using as our input into the Euclidean distance. And so what we do is basically, I just printed it out just so we can visualize it again. And we basically compute the Euclidean distance for all the content. And we basically set that equal to the Euclidean distances function that we can leverage. And now we will be calling it on the TF-IDF subset. And so, it's hard to make much sense of this, and that's only for 5 news articles, or sorry, 10 news articles, but that's kind of what the output is this massive array. So that's how we compute Euclidean distances. It's fairly nice and simple. Next, we have our cosine similarity. And so this is actually looking at the angle. So as you saw here in Euclidean distances is looking at the distance between these 2 data points or these 2 documents. Here we're looking at the angle between them. And it kind of gives you a little bit more information and is definitely more commonly used than Euclidean distance. And so again, we can import the cosine similarity from scikit-learn. And then same thing, we call cosine similarity on our TF-IDF subset. I basically get this array printed out. And again, this is quite a massive array just for our subset of documents, but this just helps to give you a sense of what does this array actually look like. And again, this is a range from 0 to 1, and so that's kind of how we will be able to tell from a scale of 0 to 1 how similar are any of these two given documents. So our third one is Jaccard similarity. And again, scikit-learn has a Jaccard similarity score. And so Jaccard, there's actually 2 options it gives for Jaccard score. You can do a Jaccard similarity score or Jaccard score. I've chosen to use the Jaccard, I believe it was the Jaccard score. And then we also need to import the pairwise distances because it actually does need to use that a bit later on. So let's just import those from scikit-learn. And so again, just for simplicity's sake, what I've done is actually just taken 2 subsets of articles along with their tokenized content, and where I have kind of assumed that there might be some similarity or overlap in their information and the topics that they're covering. So what I've actually chosen is what you can do really nicely with pandas data frames is actually choose the specific rows that actually contain a specific string. And that's how you do this. You basically will, this is a new data frame that we're creating, and basically of content df, specifically this tokenized content join column, we basically do .string .contain. So, any of those strings in those rows, if it contains Los Angeles, and it is case sensitive, so you do have to specify it like this. Remember, we lowercase everything, so it's going to be all lowercase. And then basically I'm just extracting this specific column. And so this is our Jaccard, and I basically just called it Jaccard LA because for Los Angeles or LA. And as you can see here, it has the single column, tokenized content join, a length of 771, meaning out of all these articles, 771 contain Los Angeles somewhere in that entire string, in that entire news article. And I basically repeat the exact same process, but now I'm saying, okay, do any of these strings contain California? And, Los Angeles is a major city in California, so I assumed, there might be some overlap in what these different news articles are covering and what kind of information they contain. So I call the same exact thing, but I just name it a new data frame, Jaccard CA for California. I use the specific column, and well, you'll see that originally this was a far larger data frame that we ended up with, but Jaccard score actually, it requires the same length for the 2 arrays that it's comparing. So I've actually shortened it to 771 because that's the length of the LA data frame. So if you see here, it's confirmed the length is 771, that matches. So our Jaccard score will properly work. So now let's actually compute the score. So I'm basically just calling a new variable. I'm computing the Jacquard of the content. And I basically call this Jacquard score that we imported earlier. And the two things we're comparing is Jacquard LA and Jacquard CA shortened, because remember we shortened it down to 771. And you have to actually specify this parameter inside here. So I've specified the average equals micro. There's a few other different options. And in the documentation, it specifies, when would you use a certain parameter. I've chosen micro for this case, and basically we compute that and we see, okay, it's I guess it's 0.0, but I'm not sure what the value is different here, but originally it was, not just as, a zero value, was a non-zero value. But basically it'll show you, okay, was I correct to assume that there was some overlap in information, given that California and LA are would have some relationship to each other. So just as a second example, I'm actually going to be looking at another two subsets that may potentially be similar. So here I'm looking at New York City and Brooklyn, which are two major cities in the state of New York. And I'll be repeating the same exact process of looking at all of the rows and if they contain the string New York City. And so basically what happened here was that the length of New York City was actually far larger than the one for Brooklyn, because it is a bigger city. So I actually shortened it to 476 because that's actually how many there were for Brooklyn. So as you can see here, the lengths match up, so the Jacquard score can be properly computed, and we computed that. And as you can see, this is the Jacquard score for just comparing these two different subsets of the articles. And so what you can do is, you can choose your own different kinds of subsets if you're making any assumptions of, would certain topics be related to each other. I chose, to go off of just geographical, parameters like, a city or a state, but you can go off of anything with politics or any other social issues. You can mess around with it and just explore more about the content of these articles, and you can get some pretty nice insights. So now the last two things we have for our document similarity is the clustering, and then we have our topic modeling. And so for document clustering, I'll be doing a very similar, as we saw in the theory part. I was, kind of first computing the distance and the different cluster sizes, and then plotting out the dendrogram. So I'm just going to be repeating the same process, but for our own data. So we're actually going to be using the dendrogram and the linkage packages that we get from SciPy, which is another very handy package, just like sklearn. And so basically we have to call this matrix, we have called it Z. You can feel free to call it anything else you would like. And you basically call this linkage function on our cosine content. So as you saw from above, when we computed our cosine similarity, the cosine content was this matrix that we end up with. And that's what we actually are going to be using for our document clustering. But you can feel free to use any other metric. I just have chosen cosine similarity because it's quite commonly used. And then here we specify exactly what linkage criterion we're going to be using. And as I said, we chose Ward. So we specify that here, and then we actually will turn that into a data frame where the columns are the document cluster 1 and 2, the distance, and then it's going to be printing out the size of each of those clusters. So we see our distances there. And then again, we're going to be using matplotlib to plot out our hierarchical clustering dendrogram. And as you can see, we have all these different data points, and you can see that they're sort of getting grouped up into these clusters, and it's a very nice hierarchical structure. And obviously this dendrogram will change depending on what subset of the articles you're taking. If you go over all 10,000 articles, I'm guessing this dendrogram will look a lot more complex, have a lot more levels of hierarchy, but because we've chosen this small subset, it's just a bit easier to look at and kind of visualize, okay, what clustering is actually going on here. And then next, we're actually going to be using another thing of SciPy, which is the F cluster. And basically what we're going to be doing is assigning our cluster labels. And because we're going to be needing that for our next couple of stages. So we're going to be looking at our, we're going to be using this F cluster, calling it on our Z that we created up here. And then we're going to be using our criterion is actually our distance. So basically, what is the distance between each of these clusters? And then we're going to be printing it out as a nice, nice data frame. And here you have, this is the entire thing. Obviously, our tokenized content join is our only, is our column with everything, pre-processed. But, these are just here because we just printed out everything. And then we have our cluster labels all the way from, obviously it's 10,000 rows, so you can't see all of them. But that's our cluster labels that we end up with. And then ending up from there, we get into topic modeling. And as I said, we're going to be, topic models actually use matrix decomposition. And so from that, we're actually be using the LDA method. So we first just need to import that. And then we can very easily call that. So we basically assign it LDA as its name, and then we call LDA, and we basically have set 2 parameters in here. This is basically how many iterations is it going to go through. We have 10,000, and typically want to assign this random state equal to 0. And then we end up with this document topic matrix that gets printed out, and we actually have to again call this dot fit underscore transform, and we're calling it on that x underscore bag of words that we calculated back in our bag of words implementation. And then we end up printing out our features, and basically we assign our columns from T1 to T10, basically the 10 topics, and then we'll just print that out. And typically it takes a little bit of time, so I'm gonna give that some time, but you should basically end up with the data frame that you were seeing here earlier. And then there's just a couple more steps afterwards. We're actually going to be looking at the k-means clustering. Okay, so that's printed out. And then now we're going to be looking at the different components in this LDA. So basically we have, we're looking at for all of these different weights in this matrix. And this matrix is composed of the different components of the LDA that we implemented up here. And we're basically going to be iterating through all of those, and we get this nice array. And obviously it's very large, but basically next to every single term, we get all of these values. And feel free to scroll through this and just look through it and get kind of a nice understanding about all of that. And then our last implementation will be with the k-means clustering. So in order to do that, we have to import the k-means from sklearn. So let's import that. And now we're going to be calling this k-means clustering. We're going to set the cluster 3, and again, this random state parameter equal to 0. Then we'll be calling the dot fit transform and on our features that we created up here. So we call it on that. And then basically we're going to be printing it out as another data frame. We're going to be setting our columns equal to the cluster label. As you can see here, that's what gets printed out, and that's what we end up with. So with k-means clustering, as I said, with the number of clusters that we have here is like S3. That's kind of this input parameter that there's actually a very complicated process to figure out exactly what is this optimal value. I chose 3 here. I didn't go through all of the steps of optimizing it. It's quite a complicated process, but I just chose 3 here for just simplicity's sake. And there's a lot of optimization that is done to, there's a lot of work that's done to figure out that optimal value. And so that concludes the implementation. So just as a nice review, we went through TF-IDF, bag of words, and then all these different use cases of document similarity. And on the bottom here's just some references that I used for what was gone over here, and just some further reading. So I'm just going to switch back over to our presentation, and let me just present here. So just for some homework and some additional resources, this is a nice link for just some document similarity using Python. Datamites has a nice article on just some TF-IDF and bag of words techniques that we actually we learned about, and just like some more information about those two. And then this last article was it's a very nice article where it actually goes through all the way from the pre-processing, and it has an entire pipeline all the way up to document similarity, and it's a very nice process to follow through. So I highly recommend going through that. So that's it for the additional resources. And so we're going to be having our next session next week, just at our normal time from 12 to 2 p.m. Pacific Standard Time. And if you have any questions, please join us on Slack by clicking this link here. And please post your questions to the Help Me channel. And so for next week, it's going to be part 3 of the deep dive, where we're going to be going over word embeddings, text vectors, word2vec, Glove methodology, and then we're going to be implementing with GenSim. It'll be next week, 12 to 2 p.m. PST, and we hope you all can make it. And since we have just about 10 minutes left, I'm going to go through some of the Q&A. So let me just hop on over there. Right. Let's see. And in the chat, you can see the link to join our Slack community. And please subscribe to the Help Me channel. That's where you can ask any questions about what I went over today, or even for previous weeks. If you look in the track events channel, that'll give you info on all the upcoming events. And in the NLP channel, you actually have can join a community of other learners. And so let's see, I'm just going through some of the questions. So let's see, do we make up T10, or is it given in the data set? So that's something that we typically have to make up. And the example that I went over in the presentation, it actually had these categories already assigned to the documents, and that's not a step that I chose to include. But typically, what you would do is that you would go through all the different news articles and pre-assign these categories. So you could assign it to, like, if they had like weather, food, and animals. I'm sure that's not enough to cover, all the 10,000 articles, but basically you would go through and categorize them in advance, and then see, how well is this document clustering happening? How well is this topic modeling doing? So that's how we would go about that process. And then let's see, is the document similarity used at the document level, like highlight the relevant parts of a document section? So I believe that can be done. I did not go over that in this case. That's when I was kind of going, when we were talking about the possible applications of document similarity, we can actually go through and do kind of like nice, you can basically extract the keywords that are in any document. If there's a higher occurrence or frequency of those keywords in a specific part of the document, then we know that's like more highly relevant. So that would be kind of something that we could do, and that would be I did not implement that, but that's definitely something that you can do. And then let's see. And feel free to add more questions in the Q&A box, and I can answer those. Let's see, a text data set related to COVID-19. I would suggest Kaggle, which is where we actually got the news articles data set from. That has quite a few data sets that that are, and a nice thing is that there actually are people who have, created their own notebooks doing something with a data set, and you actually can take a look, and it's a very nice open source, pool of information. And so I would highly suggest exploring Kaggle a bit more. And then let's see here. So why the cluster labels had NAN in document clustering part. So that has to do with that there was no specific cluster label that could be definitively assigned to that specific document. And that might just be due to we would have to expand the number of clusters and topics that we have pre-selected. So that would be a nice indication of we're not covering enough, and we would need to kind of and that's when it would help to pre-categorize all of the documents, and that would definitely help to make sure that you're not getting any NAN values, and you're actually properly clustering everything and assigning the proper topics to each of them. Is there any specific method to understand how many topics actually cut from the content? Understand how many topics. So I believe those are a bit more advanced. I know for topic modeling, LDA does help with that, but again, due to the range of how many 50,000 news articles that we have and how many different categories it could possibly be, how many different categories and topics, it does depend on the like diversity of your data set and like the specific tasks that you're trying to achieve. And also, as you saw, even when I specifically chose like Brooklyn and New York City, even those had a very pretty low Jacquard score, and I didn't go through it, but you can actually look through and see like what is the cosine similarity like, since that's kind of something we use more than Jacquard similarity. But yeah, it's a bit more advanced, and in the resources and the further reading that I mentioned, it goes a little bit into depth about how we choose the proper algorithm for topic modeling, because that's an entire area of research that's done in NLP. So yeah, I hope that answers your question. And then, is there any special care that's taken when you want to analyze a huge document data set like for COVID-19? So I believe you're referring to the large COVID-19 data set that's on Kaggle. And so I'm assuming that I haven't personally taken a look at the data set and what is actually in it. I believe it's a collection of research articles and other information about COVID-19. I'm guessing that something that's important to consider if it's anything with like medical information, if there's any protected information, personal information, or the idea of HIPAA and privacy and all that. So that's a very important thing to take care of. Also, when you're analyzing something like COVID-19 and there's a lot of very unknown pieces of information about COVID-19, and it would help to have experts in the field, or like doctors, medical professionals, to perhaps like inform what kind of research articles to pay attention to, and what is actually backed by evidence and what might not be. And so there's a lot of it does depend on privacy and those kinds of issues. And let's see. So K nearest neighbors is actually different than the K-means, slightly different than the K-means clustering. So K nearest neighbors is used for very nice, like as you said, regression and classification. But what we used here was K-means clustering, which actually is trying to group different data points into what makes sense for them to be grouped, and to make sure that the variance within the data points in a single cluster is as small as possible. And so that's what we're doing in this case, and our data points were the documents. And so K nearest neighbors is a similar idea, because that input parameter K is actually something very important, because it's this optimal value that we want to make sure we're using, but it is a slightly different task. Okay, so I don't see any more open questions. So I hope everyone enjoyed today's session. Please feel free to join the Slack and specifically the Help Me channel for any questions as you're looking through the slides and the implementation that we went through. I hope everyone can join us next week for our third part of the deep dive. Thank you so much. Have a great rest of your day and your weekend. Thank you so much. Bye-bye.